Alright, so in this video, I'm gonna be explaining a very beautiful article. I have a playlist for approximation algorithm, but nowadays we use graph neural networks for combinatorial optimization. Very classical things. And this paper is in 2024. So in recent years, there has been notable interest in investigating combinatorial optimization problems by neural-based framework. An emerging strategy to tackle these challenging problems involves the adoption of graph neural networks as an alternative to traditional algorithms, a subject that has attracted considerable attention. Despite the growing popularity of GNNs and traditional algorithm solvers in realms of combinatorial optimization, there is limited research on their integrated use and the correlation between them within an end-to-end framework. So the primary focus of our work is to formulate a more efficient and precise framework by employing decision-focused learning and graphs. We introduce a decision-focused framework that utilizes GNNs to address combinatorial optimization problems with auxiliary support. To realize an end-to-end approach, we have designed two cascaded modules: an unsupervised trained graph predictive model and a solver for quadratic binary unconstrained optimization. So we are dealing with classical combinatorial optimization like max-cut, min-cut, and many of these problems can be solved by GNN. So the overarching framework of our proposed involves an end-to-end decision-focused learning process. In that we have input graph, we give it to GNN, we predict, and we give it to this QBOS optimizer. And then we predict the decision, we have the decision, using the decision loss, we have a decision. And so, for example, the task of max-cut is just the maximum of x sub I plus x sub j minus 2 xi xj. We want to have a maximum cut. It means that these edges that are leaving this area S, should be maximized. And so we can see the target as a classifier. So we have the target learns a classifier, and theta denotes the parameters of classifier, and n is just the neighbors of x. So the graph layer can be updated like this. But we have some classical problems like maximum independent set, which is, by the way, very important. And so an independent set is defined such that any 2 points in the set are not connected by edges. Metroids and those things in classical computer science are very related to these independent sets. It's like a generalization of linear algebra, if you want. So do you see the flowchart illustrating the end-to-end workflow for our proposed framework using a simple example with 5 nodes? So we give it to GNN, then we have very good representation, but the objective is just any problem in classical computer science, like max-cut, anything, can be formulated like this x transpose qx. So for example, for independent set, we have another q. For max-cut, we have a different q. Just the variables, these entries in this matrix are different for different problems. So now you know why we are interested in this. we can formulate an end-to-end optimization spanning from input to the decision. Because we have a decision variable, for example, if edge exists or not, if node exists, if edge exists, so we can transform the graph, and we can have, for example, max cut or independent set, minimum vertex cover. Different problems are just related to the existence of some edges. And so we call it QUBO. QUBO stands for quadratic binary unconstrained optimization. And once we get this optimization problem, we can solve it. After we compute objective value, we can obtain an output of our framework for updating the parameters. We can then differentiate the traditional solver to build an end-to-end framework and update parameters through the solvers. So edge plus L of objective. So we say that X star is a local maxima if it satisfies these. And for 3 regular graph, when we have just 50 nodes, when we have 100 nodes, when we have 150 nodes, you see these irregular instances. And then they comparator methods, because each method, the metric is the size of cut, and larger is better. For example, for max cut on some G set instances, for example, G55 is an instance of a graph. For different methods, we have different measures, different metrics. So some visualizations of minimum vertex cover for several irregular graphs, and that's it.